So the first chunk of this, I'm going to close this now, just for everyone, don't need it. So looking at the slides, I can see here the first section is about compilation. Now, compiling code, like I'm talking about just C code here, because C is a compiled language, meaning that you write the code, you compile it and run it. Unlike languages like Python, where you write essentially a script that is then interpreted like when you run it. So there's a background interpreter for Python. It's written in C or C++, I'm not 100% sure, but it's a compiled program that reads in your script and does things based on what the script tells it to do. But Python itself doesn't directly generate assembly or machine code like C does. So the advantages of this is that you're directly generating like assembly, and therefore like your code can be optimized a lot better and it can be run a lot faster. The downside is you have this whole compilation process, but really, unless you're compiling Linux kernels or Chrome or something, compilation is usually a matter of a couple of seconds. But it has a few steps to it. And so like usually people say compiling code, but really compiling code in C is really only just the one step of it. So like when I say compiling, I'm talking about generation of object files from C files. But the entire build process is actually multiple steps. And this figure outlines it quite well. So if I get my pen, we can see that we'll just kind of work through the figure. If you look here on the left, now some of you will, after doing the Git tutorial, be have had exposure to running make. Like when we run CMake, we generate the make files, because CMake is sort of like a program that tells, oops, don't need you, go away, and that says like it tells you how to generate the make files, like what sort of files to include in, and then the make file itself is calls the compiler, like GCC, and then actually instruments the compilation and the linking of the files. So make is like the file where we can essentially script the building process, but the build process itself is made up of essentially 3 steps. Now you have like, this is like the first step really, and then there's a second step, which is sort of like this is the second step. And then you have the third step, which is essentially like this here. Now, we have the preprocessor. So the preprocessor, as I hopefully detailed, I've sort of mentioned defines and macros, is something that's very specific to the C language and the C++ language. And it's a really good feature to have, because it can mean that we can add certain things into our files, like hopefully in the Git tutorial you read about macros and defines that make our files more easy to read, or we can really simplify code generation. Like if you have an array of objects, you can make macros that do certain things, so you only have to write one line of code. Very similar to like inline functions, slightly different. We won't really go into that. But the preprocessor is a really good functionality to have to simplify a lot of things in your code and make your code a lot more elegant. But the preprocessor, in a way, can be thought of as a copy-paste. This is the most simple analogy, I think. Like if you have in your code, if you have at the top of your code, you write #define this is to make a define. And what a define is anywhere that whatever's here is found, it'll get replaced with whatever's here. So let's say this is #define, like pi. This is a really good one. So we'll write, and usually defines are written in capital letters. So #define pi, and then here I'll have 3.14, whatever it is, the rest of the numbers are, right? And so then when I'm in my code, I can say like 2 times pi, right? And I can put in here like heaps of digits. And this way, what happens is that my code is easy to read. Like here, when I look at this, I see, oh, it's 2 times pi, it's 2 pi. But really, in actuality, when I pre-process my file, like when the preprocessor runs on top of my file, it will replace every occurrence of pi with this long number, right? And so because if I was to copy and paste this, like let's say we wanted to deal with 100 digits of pi, to be fair, using a define is probably not the most efficient way of doing this. But if we want to use 100 digits of pi, every time we wanted to use pi, if I pasted those 100 lines in there, 100 digits in there, our files would be full of like these numbers everywhere. It would be super hard to read, right? But by doing this, we have this easy to read file that we then can pre-process, and it will essentially copy and paste this long number everywhere it sees pi before it compiles the file. The other advantage of a defined, for instance, is like, let's just say we broke the laws of mathematics and we decided that pi was no longer 3.14 and we wanted to make it 3.24 or something, right? So we wrote this 24. Everywhere that pi has been used, obviously when it's pre-processed, the new value is pasted in there. So you only have to change it in one place and it gets changed everywhere. So it's really good for configuration. Like if you want to have, in the free RTOS, you config your maximum priority, and then if when you're creating your tasks you use maximum priority plus or minus some number, like if you use max priority -1, then you change the amount of max priorities you have. All of these priorities sort of shift respectively without you having to go through and changing the priorities manually every time. So that's the advantage. Now I'm just going to change that back to a 1 because otherwise it's going to annoy me. But essentially this is what the preprocessor does. And macros as well, in a way, are sort of like functions that you use in the preprocessor for like code generation. They're a bit more complex. You'll see them in my code, but they kind of work along like the way, their functionality, and let's clear this, is very similar. They're also used in a hash define, but they're essentially defined where you can pass in like parameters or an argument. So let's say, a good example would be, for instance, like we'll have a macro that returns to us n multiples of pi, right? So we'd have like a macro called like npi, and then we put in here some argument and we'll call it num, right? So this is the number of pi's that we want. And our macro would essentially just be, it will return, normally good practice to put your macros in brackets because you never know where it's going to get used. And this way you're guaranteeing that like, logic doesn't mess up, or like if you have it next to a plus minus and you have a multipliers in it, if you have a plus or minus, but it's next to a multiplication operation that may be using, I don't know what you call it in your countries where you study, but like for me, it was bombed-ass or something. The order of multiplication and subtraction and stuff, you might mess it up. So usually you put it inside brackets. But then, for instance, in here, you would have like beta, pi times like multiplied by num. And so every time you use this define, I can use the define in my code by like, I'll have this, and then I want like 4 pi. So I'd say n pi 4. And when this gets pre-processed, what happens is this 4 gets substituted into num, and this entire line then gets replaced with brackets pi times 4, right? And so this is sort of like a way if you can have a define that you can interact with, right? So this is the preprocessor. And now we'll get to, so once you get your file, your C file is firstly preprocessed. And then it essentially generates this like intermediate file where everything's been copied and pasted in. And another thing the preprocessor does, which we're all hopefully very common with, is the include directive. Include. Now this works in a very same copy paste format. You can imagine whenever you have like include standard IO, like stdio.h, when the preprocessor runs, it actually goes and takes that entire file and pastes it in there. And so when you get into more advanced coding stuff, you can do things like you can actually include a C file, like you can write functions in a header file that you then include into the middle of a C file or something for some reason, because essentially it just gets copied and pasted. Now sometimes you can run into problems like circular inclusion, where files are including each other and they sort of get into this loop of copying and pasting into each other during pre-processing. And there's certain measures you can take to avoid it, but it's more just like an experience thing. But the include directive is also a preprocessor directive where like the file is copied and pasted in there, because inside of an include file you have prototypes, right? And you know that you can't use a function, like let's say you have a function prototype. You should all know that you need a function prototype above the place in the code that you're calling the function. So if your main is at the top of the of your main.c, like your main function is top of your main.c, and you have some function at the bottom, you need a prototype of it above it because of how the files are processed. It won't know it exists. And it's the same idea with includes, and this is why they're always at the top, is because the file gets pasted into the top, so they essentially paste in a heap of prototypes. Why exactly we need prototypes, I'll see a little in a second when I talk about the linker. But essentially, this is what includes do in the preprocessor. And so now we have these preprocessed files, and they need to get turned into something that we can, like, they need to get compiled, right? And so turned into assembly code. Now, the compiler works on a per file basis. So each C file gets compiled into an object file, right? And so one of these guys here. And so it works on file by file, and it will just turn straight C code into the equivalent assembly code. Very straightforward. But now the thing is that functions from this file, like from one file, will need functions from another file. And then we run into the problem that, like, and this is essentially why we need prototypes, how does this file that gets turned into an object file know that the function it needs to call is in this file over here and whatever? And so these object files have things called symbol tables, and they generate symbols, and symbols are essentially saying, hey, in my file I expose this function, this variable, this one, and then they won't know exactly where they are, but they know that they're there somewhere, right? And so if you don't have the prototype, your file will throw a compile error saying unknown function or unknown declaration, because you've not included a prototype anywhere of where this function exists. So, or that it does exist, sorry, because you don't know where it exists. This is the linker's problem, but you need to give it a prototype so that it knows this function exists somewhere, which we'll see this resolution gets done by the linker. But so when your main.c is compiled using stio functions, if you don't include the header, when it compiles, it will look for the symbol of like printf, but because you didn't include the header and therefore didn't include the prototypes, it won't know where, it won't think that this function exists because this symbol has no place, or it hasn't been defined anywhere. But then we get to the linker, and now the linker does exactly this, and then it solves these symbols by linking them together. Like it finishes these links. So like in your main, if you use printf, you'll generate an object file that says, I need the symbol for printf. If you include the include file, it will know that this function exists somewhere, like in the C library, but it won't know where. But it doesn't care. It'll just compile the main.c into an object file. And now that it's got its prototype, it'll say, yep, cool, everything's there somewhere. The linker will sort this out for me in the next step. And this is what the linker does. It will then take either the library file for standard, like in a standard library, or it will take a symbol exposed by a separate object file and put them together. And this is this linking, and this is why it's called linking. And so once you've linked all of your object files, like resolved all of the symbols and whatnot, so that essentially the object files need to know where in memory it can find these other things, because once everything's linked together, you have one sort of homogeneous bundle of stuff, and this is your binary. It's a bundle of binary, right? And so that's when you get your executable files, your shared libraries, and these are essentially things that are used at runtime. And then you also have your link map file, and so the link map file explains where in memory things are stored. So hopefully this little explanation has made it quite clear on how this process works. This is also very much explained in the Git tutorial. So now we look at an example, right? So we have a very basic hello world example using standard IO. So this is in standard IO, we have the function putS. It has all sorts of like input output standard library stuff. But so if we compile this using GCC, we generate a greeting binary. So this is our executable, and you run it by using this // right? And what we would want is that when we run it, it outputs exactly this. So echo 2 is like the return result of it. This is getting beyond probably the scope of this lecture, but ideally, essentially, it just needs to print putS hello world, right? Like we have seen here. And let's see what the next, okay, well, there's no more slides. But what the problem would be that if we got rid of this, it would try and compile this file, but then it would say, hey, I need the symbol for put S, and then it would throw you a compile error saying like, unknown definition or something, because there was no prototype included, because the include was forgotten, so it wouldn't compile. But if we include stdio, then it will link in to the corresponding shared object file that is the standard C library, where these symbols and these functions are defined and implemented. And so that's how compiling, or like better, like what we always say compiling, but really building this entire process works on C. Okay, so now we'll move on to functions. So I'll stop this one here.